right, welcome back. Here is our next bit. Now this piece here is a little bit challenging, so take some time, take a deep breath, get your calculators out, get your periodic tables out, get a drink of soda, sit back on your couch, relax, whatever you got to do, because this is a little bit challenging. This one on empirical formulas here, definitely students at first a lot of times have a little bit of a challenge with trying to figure out what this means. So like I said, sit back, get ready to watch this a couple of times so you can figure out what's going on. But empirical formulas is basically how do we figure out the chemical formula of a compound. Not just what the percent composition is, but literally what the little subscript numbers are when we start writing formulas out. And again, this is a little bit more challenging, but once you get the hang of it, it's actually pretty straightforward. So first of all, by definition, what is an empirical formula? So the term empirical actually means something that you can determine in a lab. That's what the term empirical means. I have evidence for it. And it is simply the simplest ratio of the elements that are present in there. Basically, it's the simple formula. It sometimes is a reduced formula, so I'll show you some examples of what that looks like. But it doesn't necessarily tell us everything about how a compound is put together, but it does give us a little bit more information about the formula than percent composition does. Percent composition, it's really hard to say, you know, if you know from water that it's like 12% hydrogen and 88% oxygen, it's really hard to go from that to figure out what the formula that's actually H2O. Empirical formulas, this whole process here is designed to give us a formula, not just a percent by mass. So in terms of what these things look like, don't let the word throw you off. It's actually fairly straightforward. An empirical formula is just the simplest ratio of the elements that are present in there. Many times the formulas you've been writing so far have been empirical formulas. So something like H2O or NaCl are empirical formulas for the ionic compounds and things like that that we've been doing. NaCl means there's 1 sodium to 1 chlorine. Some of them can be a little bit longer, like K2Cr2O7, potassium dichromate. That's an empirical formula. That's as simple as that formula can be to get down to give us that ratio: 2 potassiums, 2 chromiums, I don't know, anyway, and 7 oxygens. But certain compounds like hydrogen peroxide have a simpler formula, and in fact those formulas look a little weird. Like when we write H2O2, it kind of looks a little strange, and students often ask me, why don't we write it as HO? Why don't we reduce it down? Well, this is your chance. That's what empirical formulas are. It's that reduced down ratio. Now, the reduced down ratio is that simplest ratio. Sometimes the chemical formulas are different, like H2O2 has a different chemical formula. We know it's actually 4 atoms glued together than the ratio, which is 1 hydrogen to 1 oxygen. But this can be a little bit funky in terms of how these work out. So we're going to tend to see these with our type 3, our molecular compounds, like nitrogen and oxygen or carbon and oxygen. We tend to also see these in really big molecules like organic compounds, where you've got lots of carbons and hydrogens and oxygens that can be bound together in increasingly complex ways. So here's some non-examples of empirical formulas. These ones that are listed down here would not be empirical formulas, they're chemical formulas. So like H2O2, it can be reduced down to HO. N2O4 can be simplified down to NO2. NO2 is the empirical formula of N2O4. And that last one, C6H12O6, again, it can be reduced down. It's not an empirical formula, that's a molecular formula for sugar. So let's take a look at a couple of example problems for you to practice on there. So on the left is the molecular formulas, those are the chemical formulas for these things, and on the right, it's your job to kind of figure out what that simplest ratio is. So for example, for butane, which is actually C4H10, 4 carbons and 10 hydrogens bonded together, the simplest formula, the simplest ratio is 2 carbons to 5 hydrogens. That's its empirical formula, C2H5. So take a second and see if you can reduce down the formulas for glucose, benzene, and water and figure out what their empirical formulas would be. So now's a good time to hit pause, see if you can reduce those ratios down, and then we'll take a look at what they actually are. Okay, you ready? Okay, here we go. So C6H12O6, when we reduce it down, it's actually CH2O. 1 carbon to 2 hydrogens to 1 oxygen. Basically, you divide each element of that particular formula by 6 to get it down to its lowest whole number ratio, CH2O. For benzene, you've got C6H6. You would never write a fraction of 6 over 6, right? So you divide each thing by 6 to reduce it down as well, and you get the simple empirical formula of CH. For every 1 hydrogen, there's 1 oxygen. And for water, if you want to reduce that down, well, you can't. It's already reduced down. H2O is its empirical formula. It's already as reduced as it can be, and that is okay to do that from time to time. All right? Got the basic idea in terms of what those are? So why do we have to do this part? Why don't we just call them formulas? Why do we have to use the phrase empirical formulas? Well, Again, that term empirical means it was derived from lab data, and sometimes lab data can't give us the full picture of what's going on. And in this case, a lot of times when we do these types of analyses, it really only tells us the ratios of how many carbons to how many hydrogens to how many oxygens. So on the screen here, I've got some really good examples of 4 different things that would all come up with the exact same empirical formula. Every one of these has the empirical formula of CH2O, 1 part carbon to 2 parts hydrogen to 1 part oxygen. On the screen, the black ones, by the way, are carbons, the red ones are oxygens, and the white ones, or light blue, I guess, would be considered hydrogens. So if you want to count them up, you're welcome to, but you can take my word for it. So again, every one of these has the same empirical formula, CH2O, but they have different molecular formulas. This one up at the top that I just labeled here, this is lactic acid. It's C3H6O3. You can see it's kind of 3 times that molecular formula. And you know what lactic acid is if you're involved in athletics at all. It's the stuff that causes cramps, right, when you're starting to run and it hurts. You've got a couple other ones here. This one on the bottom left, the simplest one, that's formaldehyde. Formaldehyde's nasty. It's actually what we'd use to preserve dead bodies. Definitely not the same thing as lactic acid, right? But that's the simplest one. That's where the empirical formula and the molecular formula are actually the same thing. This one over in the top here, this is glucose. That's actually regular sugar like you'd use in your blood sugar, typical product of photosynthesis kind of thing. C6H12O6. It's actually a multiple of 6 times that empirical formula. And this one on the bottom right, that's actually vinegar. C2H4O2. It's acetic acid. So these are 4 different compounds, very, very different, sweet, salty, and deadly, right? Yikes. That all have some very different properties, but they have the exact same empirical formula. So it's kind of important for us to not just figure out percent composition, not just figure out empirical formulas, but sometimes we have to do a little more and figure out that molecular formula as well. More on how to do that in a later screen. So how do we do this? The whole idea with empirical formulas versus percent composition, similar sort of ideas, but percent composition is done with masses, and empirical formula is done with moles. So moles are back. Of course they are. I know you thought you were done. You're not done. So with these, you have to convert to moles first. And once we have moles, we can get a ratio from it, and that ratio will give us the formula. So it's a little bit different, and sometimes in some ways more useful than percent composition is. So here's our basic overall strategy. You're going to see me use this in the next few slides. Number 1, we're going to calculate the moles that are present of each element, and then we're going to try to find that ratio of moles. Is it 1 to 2? Is it 2 to 1? Is it 3 to 5? Something else weird. But that's the basic strategy. Figure out the moles, and then try to determine how they relate to each other in terms of a ratio. So let's look at an example problem and figure out what this looks like. So first of all, here's a sample problems given to you. We've got, what's the empirical formula of this compound? It's got carbon and hydrogen in it, 47.98 grams of carbon, 16.12 grams of hydrogen. So here's my strategy again. Number 1, calculate the moles of each element, so carbon and hydrogen. And number 2, see if I can figure out what that simple ratio is between them. It's always going to be some sort of a simple whole number, usually less than 5 or 6, but it should be a simple formula. And then that ratio then becomes our subscripts. So here's what this looks like. So number 1, I'm going to analyze carbon. Here's my little wonder fraction, figuring out how many moles of carbon I have. So I started off with 47.98 grams of carbon, and then this right here is our molar mass of carbon. So I'm dividing by molar mass in each case. So this would give me 3.995 moles of carbon would be present in this particular sample. Okay, when we deal with hydrogen, similar little wonder fraction. Again, I'm going to be dividing by the molar mass. I started with 16.12 grams of hydrogen, and I'm converting here grams to moles for hydrogen. And you can see when I do this one out, I end up with 15.96 moles of hydrogen. So what's the simplest ratio of these things? Now these numbers are both pretty close to whole numbers, like the top one's pretty close to 4, and the bottom one's really close to 16. So if I actually do that ratio, 4 to 16, I can reduce it down. A 4 to 16 ratio is also known as a 1 to 4, because both of those numbers, 4 and 16, are divisible by 4. So if I have that ratio of 1 to 4, that's now my formula. 1 carbon to 4 hydrogens, and that gives me the empirical formula of CH4, also known as methane, which is fart gas, and that's why we have the flaming cows up at the top, our number 1 contributor to global warming due to fart gas. So anyway, CH4 is the particular stuff that would make this up. Again, how many moles of each compound do I have, and then what's the relationship of moles to moles? Is there a simple whole number ratio that we can get to work with these? It takes a little bit of practice to get used to this, but once you start to see those ratios, it gets quite a bit easier. Okay, so let's take a look at an example where maybe the ratio isn't quite as obvious, and here's the trick to deal with this. So this one's going to have actually 3 different elements to it. We've got calcium, oxygen, and hydrogen, but we're going to apply the same basic idea. First thing we're going to do is try to figure out the moles of each thing. So here's my calcium work. I've divided by the molar mass of calcium. Here's attacking oxygen. Again, I've divided by the molar mass of oxygen. And then the third one's hydrogen, dividing by the molar mass of hydrogen. So here's our numbers. It's 0.337, 0.675, and 0.668 moles. Not obvious what the ratios are here. So maybe you can see, maybe you can't, but and it's okay if you can't. So here's the trick. The trick is to reduce this down, divide each one of these moles by the smallest number. This will simplify your ratio out because one of them will become 1 and then the other ones will be some multiple of it. So here the smallest number of moles I have between calcium, oxygen, and hydrogen. Smallest number is calcium, it's 337. So I'm going to divide all 3 moles by 0.337. And you'll see what this looks like when I do this out. So this is, again, it's just a math trick to see what those ratios are when it's not obvious that it's 1 to 2 to 2. So if I take all these divided by 0.337, because that's the smallest number, I get now a ratio that looks like pretty simple whole numbers to me. I get a ratio of 1 calcium to 2 oxygens to basically 2 hydrogens. 1.98 is close enough that I can round that. So I get that ratio, and that means I can now write my formula, which is CaO2H2. And that means there's 2 oxygens, 2 hydrogens for every single one that's on there. This is probably calcium hydroxide, but anyway, you don't know that necessarily. You're just going to write it out just exactly like the formula is given to you in the problem. Make sense? It's just a trick. Divide by the smallest number. So here's an example of what you would do when you can't round. I'll show you what I mean. Here's our example. Sorry, our example here. I should back up, right? Give you a chance to even read the problem. So if we've got trying to find one that's got nitrogen and oxygen to it. Same strategy, convert to moles first, and then we'll start dealing with the problem from there. So I've got 9.52 grams of nitrogen. Here I am converting it to moles of nitrogen. Here's me working with the oxygen, again dividing by the molar mass each time to get me the moles of oxygen. So I've got 0.680 moles of nitrogen, 1.70 moles of oxygen. Not an obvious ratio here. It's not like 1 to 2 or 1 to 3 or something like that. It's almost like 1 to 3, but not quite. So trick, divide by the smallest number. Again, just like I did in the last one. So our smallest number here is 0.68. I'm going to divide both of them by 0.68. That becomes a nice even 1. And that one doesn't. Darn it, that's a 2.5. So this trick will come up every once in a while. You'll start to see what I call fractionals, like a 2.5 or some other decimal place equivalent of a fraction, like 0.25 is a quarter, 0.33 is a third, 0.66. You get some weird ones on there. So if I get these weird ratios where it's in the middle, it's not obviously at the end, like 1.01 or 1.98, you're not allowed to just round it. So the trick here is to multiply by whatever that fractional is. If it's a half, multiply by 2. If it's a third, multiply by 3. If it's a quarter, you'd multiply by 4. I'm probably only going to give you a half in a Chem 1 class. Chem 2 class, they'll give you other ones, but maybe for extra credit. So if this is a half, 2.5, I'm going to multiply both numbers by 2. So in this case, I would take my ratio of 1 to 2.5, multiply everything by 2, and I end up with a ratio of 2 to 5, because 2.5 times 2 is 5. So this actually becomes now nice whole numbers, and I can use this. My empirical formula here is N2O5. Again, that's a little bit of a tricky one. Most of the problems that you're going to do are not going to be like this, where you have a weird ratio, a real weird fractional on there, but you do need to be able to deal with those. Recognize that, oh yeah, 0.5, that's a half. So I'm going to multiply that by 2 just to get it up to a round number. Okay, so, except sorry if your brain exploded. The basic trick with these is to make sure you know how many moles of each element are present. This is the idea. So start with moles, not with grams. Grams is a percent composition kind of thing. So here you're going to figure out how many moles you've got of each one. You're going to convert your masses to moles, and then you want to find the ratio of moles to each other. So sometimes it's obvious and you'll just be able to see it. If it's not obvious, you got a couple of tricks. Number one, divide by the smallest number. Divide each thing by the smallest number. And then if it's some weird fractional that comes out like a half or a third, then you just multiply it by that fractional. Multiply by 2 if it's half, multiply by 3 if it's a third, and then they'll almost always work out. So there you go. That's the basic introduction on how to do empirical formulas. The second part of this video now kind of does some of the worst versions of it, like this isn't bad enough, but it does some of the more extended versions of these kind of problems. So I'll see you again for part 2 here in just a second.